So let's take a look at our first example. We've got a sequence, it is geometric, but we've got to show in part 8 that it is geometric. So what we'll be doing here is we'll be looking at dividing one term by the prior term to see if that's a consistent ratio between them. And if it is, then we have a geometric sequence. So if we take the second term 4 and divide it by 8, we get a half. If we take the third term 2 and divide it by 4, we get a half. Of course, if we do 1 divided by 2, we definitely have a half there. And if we do a half divided by 1, we still get a half. Anything divided by 1 is just going to be itself. So we absolutely do have a geometric sequence because that common ratio is consistent. It is r is equal to a half. So in part B, we are asked to find the general term. Well, we know that un equals u1 r to the n minus 1. That's the formula derived earlier. So we know that r is a half as stated. We also know that u1 is 8. That's the first number in the list. So let's put those numbers in and we will get that general term. So u1 is equal to 8 multiplied by a half to the n minus 1. That's it. That's the general term. Part C, hence find the 12th term as a fraction. So the 12th term is going to be when n is 12. So we'll just put those numbers in. u12 is equal to 8 multiplied by a half to the power of 11. Okay, now then, because I am thinking about this and I might not have a calculator with me, is there anything I can do to make this a bit easier for myself? Well, I could write 8 as 2 cubed, and I could write that half as 2 to the minus 1. So 2 to the minus 1 to the 11 is 2 to the negative 11. So actually this term will be 2 to the negative 8. It's a little bit easier to work out as a fraction. It's 1 over 256. There we go. Okay, let's try a slightly more complicated example now. So we've got another one. A, same as before, show that the sequence 8, 4 root 2, 4, 2 root 2 is geometric. Okay, so we'll look and see if we can find that same division. Is it consistent every time? So 4 root 2 over 8 is our first one. Well, that'll simplify down to root 2 over 2. 4 divided by 4 root 2. Now, we can definitely write that as 1 over root 2 by cancelling the 4's, but we'll need to rationalise the denominator by timesing by root 2 over root 2, which is root 2 over 2, and that's the same as the first one, isn't it? And then finally, we've got 2 root 2 over 4. Well, we'll cancel the 2 and the 4 to get root 2 over 2. And yes, we have a geometric sequence because we have that same common ratio. R is root 2 over 2. Okay, part B. Hence, show the general term of this sequence is un equal to 2 to the power of 7 over 2 minus a half to the power of n. Looks complicated, I'm sure it's not. So we know that u1 is 8 as well. Let's write that down. And we have our general formula we can start plugging into, and that is un equals u1 r to the n minus 1. So let's plug those numbers in and see what happens. So un will be 8 multiplied by root 2 over 2 to the n minus 1. So what we've got to do here is work on that to try and get that to be our aim, which is given to us in the question. Okay, well, I'm recognizing a lot of powers of 2 here, so my first strategy is going to be to try and write everything as a power of 2 and then try and collect up those exponents. So the 8 is 2 cubed. Root 2 over 2, well, that's quite tricky. We can certainly work it out, though. Root 2 is 2 to the power of a half, and think of it as timesing by a half, right, as dividing by 2. So it's timesing by 2 to the minus 1, and that's all being raised to the power of n minus 1. Okay, now then, from there, perhaps we can rewrite that. So we're going to have in that bracket 2 to the negative a half to the power of n minus 1. And now we can expand that. Look, we've got a exponent of an exponent, so we can multiply those together. We're going to have 2 to the power of minus a half n plus a half. That's minus a half multiplied by n minus 1. If we now add those exponents together, because they have the same base, we're going to have 2 to the power of minus a half n plus the half, and we've got the 3 we can add. Okay, now then, we're almost there. Let's just bring that half and that 3 together. So written with a common denominator of 2, we would have, if we combine them, 7 over 2. So we've got 2 to the 7 over 2 minus a half n, and that is exactly what we should have as given to us at the beginning of the question. So there we go, we're done. Right, take a look at this example. And of course, feel free to pause the video at any point and have a go at these questions yourself. So we've got consecutive terms in a geometric sequence, and we're asked to find an unknown. So let's set ourselves up an equation. If they're consecutive terms in a geometric sequence, then if I take one term and divide by the prior term, it should always be the same, r. Well, that means that 2k over k minus 1 should be exactly the same as 21 minus k divided by 2k. That's our setup. So now if we simply try and solve this equation, we should be in a good place. Let's get rid of the fractions first. We'll have 4k squared equals 21 minus k minus 1 if we cross multiply. Let's expand those brackets next. 4k squared is going to be 21k minus 21 minus k squared and plus a k. And then let's try and collect these up and put one side equal to 0. I think I'll put it all on the left-hand side, making the k squared positive. We'll have 5k squared minus 22k plus 21 is equal to 0. So now it's simply a case of having a quadratic to solve. I use a target number method to factorize these. If you don't know my method, you can look it up on one of my prior videos. But we say the target number is 105. That's the first coefficient times the last. That we have two numbers, minus 15 and minus 7, that multiply to make 105, add to make minus 22. So 5k squared minus 15k minus 7k plus 21 is equal to 0. Factorizing the left, 5k, k minus 3. Factorizing the right, minus 7, k minus 3. So if I have 5k multiplying k minus 3 and minus 7 multiplying k minus 3 overall, I have 5k minus 7 multiplying k minus 3. So that gives me two possible solutions. Either k is 7 over 5 or k is equal to 3. Okay, so there we are. Right, we'll carry on. Let's do another example. Okay, so this time we have a geometric sequence and the second term is given and so is the fifth. So can we write some statements about that? Well, u1r is the second term, so that's minus 6. And the fifth term is u1r to the power of 4, and that is 162. And it's again, simultaneous equations. I would prefer, though, to write one inside the other. And what I mean by that is let's take that right-hand side there and write it as u1r times r cubed equals 162. It's still the same thing. And now I can take my original one and swap it in, look. So minus 6 times r cubed is 162. Dividing both sides by minus 6, r cubed is negative 27. Cubing, r is minus 3. Once we've got that, it's very easy to find u1. We're just going to imagine going back to our original and imagining that r is minus 3. Well, u1 would have to be 2. So un is going to be 2 multiplied by minus 3 to the n minus 1. Okay, one more example. Let's take a look at this one. So we've got a sequence and we want the first term that is over 1,400. Now, you're going to need a graphical display calculator for this, and you're going to input the general formula into that graphical display calculator and use perhaps a graph or a table to help you to do that. And that won't be on this video, but we'll get the setup understood. So first of all, U1 is 6, and we've got to just work out what R is. R is going to be, of course, root 2. How do I know that? Well, look at the second term. It's 6 multiplied by root 2. By definition, R is root 2. Okay. Now we've got that, let's set up our formula for UN. So UN is going to be 6 multiplied by root 2 to the n minus 1. And all you need to do is go onto your calculator and input a function for me. So you will write something like this. F of x is equal to 6 times root 2 x minus 1. So model the function. And perhaps I would then either use the table, or you could use another function, define another one to be 1,400. And then you could find the intersection point. And the next integer value after that intersection point is going to be your answer, right? So you can do it quite easily. So you look it up on your calculator, you'll end up seeing that U17, the 17th number, is a 1536. So therefore, n is 17 is the number, and 1536 is the term. Okay, that's enough of those. We're now going to have a look at some applied questions. Okay, so here we have a growth question, and what we're going to do, as soon as we see that, we're going to just make sure we're using a slightly different formula. So I'm going to be using the UN equals U0 R to the n formula here. Okay, where, and it says in this question, my initial population U0 is 50, and if I've got a percentage there, look, a percentage increase of 7% each week, then I've got a R value of 1.07. We're talking about weeks here, just bear that in mind. Sometimes it might change, but we're looking at working out how many rabbits are present after 15 weeks. So in part A1, we've got n is 15. So if n is 15, then let's set this up. U15 is going to be 50 multiplied by 1.07 to the power of 15. And if we work that out, we're going to get 138. Right, part 2, 30 weeks. So exactly the same information, but this time n is 30. So U of 30 is 50 times 1.07 to the power of 30. Work it out. We're going to have 381. Okay, and just like last time, when we are looking to see how long it will take to reach 500, if we want to avoid using logarithms, we can easily put this up on our graphical display calculator. Just create a function that models that equation, right? So f of x is equal to 50 times 1.07 to the power of x. If we're using our calculator function mode, I would use a split screen table and then figure out what that is. You can look it up, and after 35 weeks, you're going to see that the population is 534. So our answer, look, 35 weeks.